In this video, we're going to talk about the convolution of two different functions. We actually have three different goals. Our first goal is to simply define what the convolution of two functions is. Then I want to investigate what several common properties of convolutions are going to be. And then finally, and this is really the goal here, is how can I use this new operation on functions called the convolution to help me solve problems of inverse Laplace transforms. Indeed, we're going to see that this idea of convolutions is going to play very nicely with the idea of Laplace transforms. Okay, so how should we define it? The first thing I want to think about is that if you have a function f and a function of g, there's a couple different ways you could combine those two functions. For example, you could take f and then you could add to it the function g. Or you could take the function f and you could multiply it to the function g. What I'm going to give here is a third way that I could combine functions, and it's called the convolution. We denote it with a star. So this notation is read the convolution of the function f of t with the function g of t. This star that I have here is not the same thing as multiplication. This is a new operation, something new that takes two different functions and combines them to give a third function. The way this is defined might seem at first kind of weird. It's defined to be this particular integral. It's an integral from 0 up to t of f of tau, tau being a dummy variable of integration, times g of t minus tau, and then all integrated with respect to tau. If I look at this right-hand side, well, all of this together is just some function of t. The taus are integrated out, and that there is a t first inside of the g, but also secondly in the limit of integrations, integral from 0 up to t. So there's two different places that t remain, and nevertheless it's a function of t. As long as I presume that my f and my g are actually able to be integrated, then I have this nice object called the convolution. Now in this video, I'm not going to describe why I might have thought to consider this particular object, but I want to study its properties and see how it's going to be so useful to us nevertheless. And indeed, anytime I come up with a new operation, for example, maybe in linear algebra, you figure out how to do matrix multiplication, you should ask, well, what kind of properties does that new operation have? This one has several. The first is that it plays nicely when you interchange the order. It has a commutativity property, that the convolution of f and g is the same thing as a convolution of g and f. We're going to prove this property in a moment, but let me state the second one, which is going to be an associativity property. The convolution of f with the convolution of g and h is just the same thing as the convolution of f and g, and then you take the convolution of that with h itself. That is an associativity property. And then finally, we also have a distributivity property, which is that convolutions and normal addition of functions also play well together. So if you take the convolution of the sum of two things, you can distribute the convolution, as they say, over the addition of functions, and you get the convolution of f with g, and then you just add to that the convolution of f with h. I'm just going to prove the first of these three properties for you, and then I'll leave the second two as a reasonable exercise. You can pause the video and attempt it yourselves. So the first one, the commutativity one, I'm going to begin with the convolution of f of g, and I'm going to try to alternate it around. Basically what I want to do is interchange the role of f and g here, and I'm going to do that, well, just with the substitution. So I'm going to define a new variable u, which is this difference, this t minus tau, and I'm going to take this change of variables and plug it in. So if I do that, it gives me the following thing. Several things have happened here. The g of t minus tau has turned to a g of u. The f of tau turns into an f of t minus u. The d tau turns into a negative du. That's why there's this negative sign out the front. And then finally, limits of integration change. If you plug in tau equal to 0, you're going to get u equal to t. And if you plug in tau equal to t, you're going to get u equal to 0. So that's why we have these limits of integrations going from t on the bottom to 0 on the top. It's interchanged. Okay, so what can I do? Well, I see there's a negative out the front, and so I can use a negative to interchange limits of integration. So doing that is just going to give me the integral from 0 up to t of this expression. And the second thing I'm going to do is I'm going to alternate the order of the f and the g, just change which comes first and which comes second. And the point is this. With those rearrangements, the integral that I have is now exactly the same as the convolution, but with f and g interchanged. That is, this is just the convolution of g with f as opposed to the convolution of f with g. Nevertheless, we have this commutativity property. So as I say, that is the proof of the first property, and then the proofs of the other two properties I'll leave as an exercise for you if you wish to pause the video before continuing. The final property is going to be, in some sense, the most important. It's how do I interact with Laplace transforms? Now, before I talk specifically about the convolution, I want to observe that Laplace transforms plays nicely, for example, with the addition of functions. There's this sort of linearity property that says that the Laplace transform of a sum is just the sum of two different Laplace transforms, the Laplace transform of f added to the Laplace transform of g. Indeed, if you want to put coefficients a and b in front of those f and g, we also have linearity there as well. However, the same kind of property is definitely not true when it comes to multiplication of functions. That is, you might have guessed that if you took the Laplace transform of a multiplication f times g, that would just be the Laplace transform of f times the Laplace transform of g, but this is not true. This is perhaps to be expected. We know that the derivative of a product is not the product of the derivatives, it obeys the product rule. We know that the integral of a product is likewise not the product of two different integrals. There's the integration by parts formula for that. So the point is we should not have expected the Laplace transform, which is some sort of integral formula, to work out nicely for products, and indeed it doesn't. But it does work out nicely for convolutions. That is, if instead of f times g, I take the Laplace transform of f convoluted with g, then it is just going to be the Laplace transform of f multiplied by the Laplace transform of g. So it's worth noting that there's really two different operations here. There's this star, which we use to denote convolution, that particular integral. And then there's also juxtaposition, which we use to denote just normal old multiplication, like 2 times 3 is 6. So the right side of this expression is just normal multiplications of functions, where the left-hand side involves the convolution of two functions, this new and more complicated operation. I might wish to use the standard names that the Laplace transform of little f is big F of s, and likewise the Laplace transform of little g is big G of s. In that case, the formula would read that the Laplace transform of little f convoluted with little g is just going to be equal to big F times big G. And this is perhaps best stated when I actually am asking not about the Laplace transform, but the inverse Laplace transform. That is, if I take this statement and go the other way around and apply the inverse Laplace transform to it, then, well, the inverse Laplace transform of a multiplication of functions is therefore going to be the convolution of the little f and the little g, the inverse Laplace transforms of the big F and the big G, respectively. The reason why it's so nice in this form is that if you're using Laplace transform to solve a differential equation and somewhere you get a product, the big challenge is trying to find the inverse Laplace transform. But now I know how to find the inverse Laplace transform of a product. Well, it's going to be this convolution. All right, so let's see an example. Here I'm asking to find the inverse Laplace transform of this particular function 1 over s squared plus 1 all squared. And perhaps the first thing I'll do is just sort of rearrange it to more explicitly look like the product of two different functions. Namely, there's 1 over s squared plus 1 and then multiplies another copy of that. Now, these two different factors that are being multiplied are ones that I hopefully recognize. That individually, they look like the Laplace transform of sine, and they're both the same. So it looks like I've got the Laplace transform of sine multiplied by another copy of the Laplace transform of sine. Now, as mentioned, the Laplace transform of a product is not just the product of the Laplace transform. So the answer to this is not just sine squared, as much as we might wish it to be. However, what we've just seen is that the inverse Laplace transform of a product is the convolution of the inverse Laplace transform of the two different factors. That is, this is sine of t convoluted with sine of t again. Okay, well, now I have something that I actually can compute, because the convolution is a defined thing. It's this particular integral, the integral from 0 to t. We'll take the first function sine and write sine of tau. We'll take the second function sine and write now sine of t minus tau and integrate all this out with respect to tau. And so now it's just a computational question. It's a question of, do we know how to compute this integral? There's maybe one trick to it. Notice that these two signs multiplied together have different arguments. One's tau and one is t minus tau. So I want to try to separate these a little bit. And I have actually this trig identity that I can use, this identity on the product sine of a times sine of b. So if I plug that in where a is tau and b is t minus tau, then what I'm going to get is 1/2 the integral from 0 up to t of cosine of 2 tau minus t minus cosine of t, all of that integrated out with respect to tau. And now this is an integral that I think you know how to do. I'll just move it up over here and put out the final answer. If you want to work through it, you can. So what's the point? We have defined this thing called the convolution. And the convolution had all these different nice algebraic properties, and in particular played very nicely with inverse Laplace transforms. And as such, when you're given an inverse Laplace transform that is a product of multiple different things, we now can invert it by just computing these integrals that represent convolutions.